In this lecture, we will be introducing the concept of polar coordinates. So far, we are used to looking at a point, call it P, in the xy plane by measuring how far from the origin we are along the x-axis and how far from the origin we are along the y-axis. And we represent our point as xy, and we call these either Cartesian or rectangular coordinates. And so think rectangular coordinates because we are measuring the distance from the origin in this rectangular way. We go to the right along the x-axis and up along the y-axis, and you have a right angle between the x and y axes. We have different ways that we can represent points in the plane. And another way that we can represent this point P is with polar coordinates, and polar coordinates are an ordered pair called r theta. And the way we set this up is first we label the origin as the point O, and then we think about connecting the origin to the point P. And we're going to use this connecting line segment in the origin to define a coordinate system, an alternate coordinate system for this point P. So the first thing we define is r. And r will be this distance. So r is the Euclidean distance from the origin to the point P. Once we have that, we then define theta as the angle between the line segment OP and the positive x-axis. And this is an alternative way to represent the location of this point P in the xy plane. Now, this is a little bit complicated by the fact that a polar coordinate representation of a point is not unique. So let's come back to our point P. And so our point P, we have x and y. And we're also representing it as r theta in polar. And so let's draw this ray again. So in our definition, this is the ray OP. And again, the same kind of picture before. This angle is theta, and then the length of OP is our coordinate r. But think about your radians. And think about the fact that if we took this point P and rotated it around by another 2 pi radians, we get back to where we started. So we could also say that in polar, this could have been written as r and then theta plus 2 pi. But we could have gone around twice. We could have gone around 2 pi and then another 2 pi. So we could have also written this as r theta plus 4 pi. And then we can see, if you keep doing this, it could have been theta plus 8 pi, 6 pi, 8 pi, 10 pi, any even integer multiple of 2 pi. We could have gone the other direction as well. We could have gone a negative 2 pi or minus 4 pi. So this is an issue that rectangular coordinates do not have. The point r theta is going to be the same. It's going to be the same point that we would get if we add any integer multiple of 2 pi to its angle theta. This also comes up because r does not have to be positive. R can be positive, of course, 0, or negative. And the way we handle a negative r is as follows. So let's draw our same point P. And again, we have our ray from the origin to P. And we said this was r, and this angle here, theta. So this point here, represented in polar, again, is the point r theta. If we want the point negative r theta, so let's call it Q. So we're going to have the same theta, but in this case, we have a minus r. And the way you get to such a point is you plot the point r theta where r is positive. So think of this, in this picture, think of r as being some positive number. So think of it as being something like 3. So if you want to plot negative 3 theta, what you do is you first plot 3 theta. So here you would have your distance 3, or your distance r, and theta. But then you, to get the negative version of r, you reflect it through the origin. And so this point Q would show up down here. And again, the idea is this is your point negative r theta. So to get negative r theta, you plot r theta, and then you reflect through the origin. And you can see that this also introduces some non-uniqueness, because think about taking this point Q, which we have represented in polar here as minus r theta. We could actually get this over to P by adding pi radians. So we could rewrite this point P as negative r theta plus pi. And again, the idea there is you're taking this point Q, negative r theta, and you're adding pi radians to the angle, which brings you over here. So we can see, because of these complications, polar representations of points in the xy plane are not unique. In fact, every point has infinitely many polar characterizations. Let's just get at least one example under our belt. If we want the point 1 pi over 4, this is a polar representation. So this means if this is our point P, so P is a distance 1 from the origin. So we might, to help guide us, draw the unit circle, and we know that it has to be on this unit circle. So if that unit circle, we're saying it's 1 for its radius, and pi over 4, that's the angle of 45 degrees. So we know if we draw our 45-degree line, this gives us our theta of pi over 4. And so our point P would appear here. And again, we can look at some of the alternate ways to represent this point. So we could also represent it as 1 pi over 4 plus 2 pi. Or if we do pi over 4 plus 2 pi, we can rewrite as 8 pi over 4. So this would be the point 1, 9 pi over 4. Or if you wanted to reflect through the origin to get our point Q, like we had in the previous picture, Q, we could write as, we go to the point P, so we're a distance 1, and an angle of pi over 4. But when we reflect through the origin, we get an r of negative 1. And then similarly, if we wanted to then rotate this q pi radians, that would get us back to P. And so we know that another version of P would be an r of minus 1, pi over 4 plus pi, or negative 1, 5 pi over 4. So this is another way to represent P. So this gives us a little bit of a feel of how to work with polar coordinates. And again, what makes it a little bit tricky is that you have these non-unique representations. Well, we want to also address the way that we translate between polar coordinates and rectangular coordinates. So let's come back to our picture where we have our point P, and we'll say we have coordinate x and y. So in rectangular, we write this as xy. Okay, let's connect with this line segment. And let's label things. So we have our theta is here, and this line segment OP has length r. So this is basically the labeling we have. But let's now think about this as a triangle. So let's think of the triangle here. And let's use what we know about trigonometry to define some relationships. So first, we know that in this triangle, its height is y, its width is x, and its hypotenuse is r. And so we have certain relationships between these things. First off, the quickest one is the Pythagorean Theorem. We know, because that's a right angle, x squared plus y squared equals r squared. So there's one equation that will relate polar and rectangular variables for your rectangular and your polar coordinate representations. Well, we can then think about our trigonometry rules. So think about our SOHCAHTOA rule. We know that the sine of theta is the opposite over the hypotenuse. So we have sine of theta is y over r, or multiplying both sides by r. R times sine of theta equals y. Another equation relating a rectangular coordinate to polar coordinates. Well, we can also use the cosine rule. So cosine of theta is the adjacent leg over the hypotenuse. So we have cosine of theta is x over r, and multiplying both sides by r, we have r cosine of theta is equal to x. And then finally, we have the tangent rule. Tangent of theta is opposite over adjacent, and so we have tangent of theta is y over x. And these are the four equations that allow us to change between polar and rectangular, to change expressions in polar to rectangular, or to change expressions in rectangular to polar. And so they're summarized here, and these are really the key relationships that you should know between polar coordinates and rectangular coordinates, but they can be quickly derived from using your triangle here. And we'll look at some, in a later lecture, we'll look at some ways to deal with graphs and with changing from polar to rectangular or vice versa, these different expressions and equations. But let's just look ahead a little bit and think about this issue. Graphing in polar becomes a bit tricky because of the fact that the polar representations of points are not unique. And so the way that we have to define a graph is in the following way. The graph of a polar equation is the set of all points P such that P have some polar coordinate representation satisfying the equation. So when we write down a polar equation, you may have some points where some polar representations of the point satisfy the equation and some don't. So we have to do a little bit of work in terms of polar graphing, which we'll explore in quite a bit of detail in a later lecture.